Did you ever have a math teacher who told you that you needed to memorize things because you're not going to walk around with a calculator in your pocket? Well, surprise, we all do. But the calculator as we know it is a relatively modern invention. Astronomers hundreds of years ago were, in fact, not walking around with digital computers in their pocket. So what did they do if they needed to do something like calculate the sine of an angle? One answer is that they could have looked up the value in a sine table. But there's another option. To explore, I've come to the Rare Book Room in the Linda Hall Library in Kansas City, Missouri, to examine a work from 1534 called Instrumentum Primi Mobilis by Peter Apian. This book describes how to make an analog calculator capable of determining certain trigonometric functions. But how well does it work? To find out, I followed Apian's instructions and built one for myself. So, come with me as we explore how Peter Apian says we should do math pertaining to astronomy before the telescope. Peter Apian was an astronomer living in the first half of the 16th century in modern-day Germany. He studied under George Tanstetter at the University of Vienna, which gave him an appreciation for both astronomy and cartography. This was the age of exploration, and printed maps were becoming extremely popular, which may have been what led Peter and his brother, also named George, to set up a print shop in Ingolstadt in the 1520s. One of the first books Apian printed was the Cosmographicum Liber. This book was a primer on astronomy and its use for navigation. The work reportedly became a favorite of Holy Roman Emperor Charles V, and that's precisely what Apian would have been after. This is because printing was still an exceptionally expensive business at this time, and as a result, few authors actually turned a profit by selling their books directly. Rather, authors would dedicate their book to potential patrons, hoping that they would fund future endeavors. While I don't have any evidence that the Cosmographicum Liber secured Apian direct patronage at that time, we do know that Emperor Charles did grant Apian a privilege, essentially a medieval copyright, in 1532 for a large number of upcoming titles. And indeed, the statement of this privilege is printed in Apian's book on the Instrumentum. Interestingly, listed amongst them is a work described as Astronomicum Imperiatorum, apparently a working title for Apian's masterwork, which he would publish in 1540 and would ultimately be called Astronomicum Caesarium. But adding to the evidence that Apian had not yet secured a royal patronage, we see that Apian is dedicating Instrumentum Primi Mobilis to a prince and bishop named Christoph von Stadion. The book even features a beautiful woodcut illustration of von Stadion's coat of arms. The book itself actually contains two texts. The first one is the true text on the Instrumentum Primi Mobilis, but the book is also bound with the first printed edition of Jabir ibn Aflah's On Astronomy, which had been translated into Latin by Gerard of Cremona in the 12th century. However, it's not what we're here for. The Instrumentum portion of the book is a collection of 100 pronouncements. The first of these is a set of instructions on how to build the instrument. The remaining 99 are various astronomical applications that might make use of it. But let's begin by exploring the instrument. I didn't get a good video of me doing the initial layout, so I'll have to illustrate digitally, which is honestly probably for the best. First, Apian says we need to draw a straight line roughly the size of the instrument we want to create. What Apian doesn't say, and I learned when doing my mock-up, is that we're going to need to leave a little bit of room around the edges. I was using a 12-inch by 12-inch square of brass, so I started my line half an inch away from both edges in one corner and made it 10 inches long. This line gets called AB. Next, we draw a perpendicular line from A of the same length, creating line AC. We'll then use a compass to turn these two lines into a quadrant of a circle. Apian notes that this line should be made as faint as possible, as we're going to want to erase it later, and if it's scribed into the metal too heavily, it's going to be difficult to remove. With this quadrant laid out, we then divide it into individual degrees. Apian gives instructions on how to do this, saying we should first divide it into 3 equal parts, and then each of those parts into thirds, each of those parts in half, and then each of those into fifths. Unfortunately, I couldn't find a good way to geometrically perform that second division into thirds that didn't involve making marks way off my sheet of metal. So I changed up the instructions a bit and first divided the arc in thirds and each of those into half. This could be done geometrically and with a high degree of accuracy. From there, I walked my dividers, guessing at the correct width and making small adjustments until each segment was divided into thirds, and then repeated that for the final fifths. Either way works because multiplication is commutative. Again, these marks should be made lightly as we don't want them visible on the final instrument. Next, we divide lines AB and AC in half, creating points D and E, respectively. We'll use those as the centers of new semicircles of radius DA and EA, which intersect at F. This gives us the 90-degree arc and 2 180-degree arcs, which form the fundamental arcs of this instrument. But the next step gets weird. Apian says to draw a line DE and to find its center, which is where it would intersect a line drawn from A to F, which we'll call G. Then we'll use a compass, putting the fixed foot at G and, beginning with the other foot at B, draw an arc from B to C. What Apian tells us is that after all the work we did putting in the individual degrees on that 90-degree arc, BC, we're going to have to project them onto this new arc. Fundamentally, this serves no purpose. All it does is change the overall shape of the instrument. But why would Apian want to do that? The answer has to do with the dedication to Christoph von Stadion. If you remember the heraldry presented in the front of the book, it has these weird shapes on them. These are known as hameçons de loup or fers de loup in French, and they're part of medieval wolf traps. These would be placed over strong branches on a tree, and a chain would be hung from it. At the other end of the chain would be a Z-shaped metal hook with a piece of meat on it. This would be kept several feet off the ground, so the wolf would have to jump to get the meat, at which point gravity would ensure the hook would be firmly embedded. Pushing the 90-degree arc out like this is intended to make the profile of the instrument reflect the heraldry of this potential patron. This was not Apian's first time creating an instrument to mimic the heraldic charges of a potential patron. A year prior to writing this book, Apian published Folium Populi, in which he described a sundial in the shape of a poplar leaf. The poplar leaf was found in the heraldry of the person to whom Apian dedicated that book, Johannes Guglielmi. And in the introduction to that book, he states that he had previously created yet another instrument which could calculate conjunctions and oppositions necessary for eclipse prediction. He did this using the heraldry of the most illustrious princes and dukes of Saxony, although he does not provide names. Returning to the Instrumentum Primi Mobilis, after Apian makes the instrument conform to the heraldry of that potential patron, he instructs us to make a few arcs outside of the one we just made to serve as channels for the scale's markers and inscribed values. Once that's done, we can transfer the degree marks from the 90-degree arc onto this one using a straight edge from A through each of them and making the marks longer for each fifth degree. Now we need to add the scales on the 180-degree arcs. To do this, we begin by dividing lines AB and AC into 100,000 parts. Kind of. Apian admits that this is impractical and that each mark should represent 100,000 parts, so we really only need to divide these lines into hundredths. This time, Apian doesn't tell us how, but since I'd already divided lines in half to find points D and E, I divided each of those segments in half again to get fourths, and then divided each segment into fifths, twice, again by walking the dividers. These then get projected onto the circular arcs by using a compass. The fixed foot gets placed at A, and then we place the other foot on one of the points and fix the compass's width. We then rotate it to the arc centered on the midpoint of the line we're working from, and do that for each of the points along both lines until the scales are complete. We'll also add some channels interior to each of these arcs on which the scale, divisions, and values will be placed. And aside from labeling each of these scales, that's about it. So now that we've gotten laid out, what exactly does it do? The name Instrumentum Primi Mobilis translates as instrument of the first motion. Lurking behind this is the Aristotelian assumption that the natural state of objects is to be at rest. This conflicted with the eternally moving cosmos that astronomers observe. Thus, they posited that there was a special sphere which was the cause of this motion. It was the prime mover, the Primium Mobile. This was generally placed outside the sphere of stars, but philosophers debated whether it was the 9th or 10th sphere, due to sometimes inserting a biblical sphere of water. So what the name is suggesting is that this tool is capable of calculating all of the motions of the cosmos caused by this sphere. A rather audacious claim. In reality, this tool is simply used to calculate 2 trigonometric functions that are quite useful in astronomy. But you may not have heard of one of them. When you think of trig functions, you probably think of them in the context of a right triangle with an opposite, adjacent, and hypotenuse as the sides. There's nothing wrong with that interpretation, but Apian describes things a little differently. Specifically, he imagines a circle with a radius. If we take a point on that circle at some other point than the radius, connect that point to the center, and then draw in a line from it perpendicular to the first radius, we get a right triangle within a circle. We still have the usual sides within this triangle. You can get the opposite side using the sine function and the adjacent side using the cosine. But we also have this piece hanging around outside of the triangle. It turns out that this bit is also a trig function with a special name. It's called the versus sign, or versine for short. And assuming that the circle in question is a unit circle, it's 1 minus the cosine. However, as we saw, Apian declares his unit circle to have a radius of 100,000 parts, so in his system, it's 100,000 minus the cosine. As a fun fact, there's lots of other pieces you could add to this diagram to get a whole bunch of trig functions we don't talk about these days. But we don't need to go into all that right now. What's important is that there's a forgotten trig function known as the versus sign, which is what the 180-degree arc along AB will represent. The other arc along AC will be the rectus sign, which means the upright sign, and is the normal sine function we're all familiar with. Now that everything is laid out, we can actually make the instrument. But simply lightly scratching the values into the metal wasn't enough. A real instrument would have been engraved. We know this because there's an extant instrument in the Museo di Galileo in Florence, Italy. This one wasn't made by Apian, but by Ignazio Danti, an Italian astronomer, as a gift to the Grand Duke Cosimo de' Medici I. That's probably part of the reason that the instrument is so heavily decorated. But the decorations and cutouts also serve to hide those faint scribe marks we want to obscure, making the decoration functional as it is beautiful. So let's have a quick montage of me finishing things up, and then we'll explore how it's used. To use this instrument, we'll need to draw a straight line from point A through the outer degree scale. This could be done with a straight edge, but Apian instructs us to use a thread. This is quite practical, as using a straight edge, like a ruler, blocks the scale on one side, making it harder to read. To help facilitate the use of a thread, I left a bit of extra metal around the edge so I could drill a hole at point A for this thread to pass through, even though Apian doesn't tell us to and the Museo di Galileo instrument doesn't have this. Once the thread is pulled taut, we can examine where it crosses either of the scales. We then read off the value. But you'll probably notice that the values I put here don't make much sense. The sine function, as we know it, has a range of 0 to 1 between 0 and 90 degrees. But this one goes from 0 to 100,000. Again, this has to do with how Apian instructed us to lay out lines AB and AC, dividing them into those 100,000 parts, meaning it goes from 0 to 100,000, since that's the size of the unit circle Apian devises. Thus, we can switch from Apian's scale to the one we're familiar with just by dividing by 100,000. In other words, we can just imagine a decimal point before any of the numbers presented on either of these scales. Let's take an example. If I were to look for the rectus sine of 65 degrees, I find that it crosses the rectus scale at 90,600. If this is divided by 100,000 parts, which defines the unit circle in Apian's system, we find a rectus sine of 0.906, which is exactly correct. Similarly, the thread crosses the versus sine scale around 58,700. Again, dividing by 100,000 gives us a versus sine of 0.587, and if we take 1 minus this value, we find the cosine, which is 0.423. Conversely, the instrument can be used in reverse to determine the angle if the rectus or versus sine is already known. This is done by extending the thread to the outer scale and moving it until it crosses the sine scale in question at the value desired. Then the angle can be read off the outer scale. It should be noted that the level of precision that I have given here, 3 decimals, is overstated in my opinion. Each division represents 1/100th of the scale, which means that 2 decimals is the accuracy of the instrument itself. Due to the reasonable size of these divisions, it's tempting to believe that we could easily estimate an additional place. But due to the nonlinearity of the scale, estimating the actual proportion is more challenging than it would otherwise appear. As such, my feeling is that this instrument is more of a fancy mathematical toy, meant to impress a patron than a practical instrument. Using a sine table is much more reliable, and it's not like this instrument is any more portable, which is probably why Apian provides a sine table anyway. But perhaps I'm just being overly cautious. To find out, let's examine some of the other 99 pronouncements that Apian gives, which make use of these trig functions. In each case, Apian provides an example problem in which he uses the sine tables, so we can compare what we arrive at using the instrument to his values using the sine tables. Here's one on how to determine the declination from the celestial equator of any point along the ecliptic. Apian tells us that determining this is one of the most frequent astronomical calculations. Indeed, this value is so important that it is the first table Ptolemy calculates in the Almagest, after establishing his table of chords. So let's take a look at Apian's example. Apian uses the position of the sun on the date that Christoph von Stadion was made a bishop, July 5th, 1517. On that date, he says, the sun was 2 degrees and 26 minutes into Gemini. To perform the calculation, we need to determine how far away that is from one of the equinoxes, which are at the beginning of Aries and Libra. Aries is the nearer of these, and Gemini is the third sign. So we have 30 degrees in each of Aries and Taurus, and then the 2 degrees and 26 minutes that the sun is into Gemini, making it a total of 62 degrees and 26 minutes from the vernal equinox. Apian instructs us to take the sine of this and multiply it by the sine of the obliquity of the ecliptic, the angle between the celestial equator and the ecliptic. Apian gives a value of 23.5 degrees for that. So, using our instrument, let's find the sine of these two angles. To find the sine of 62 degrees and 26 minutes, we'll pull the thread from point A across 62 degrees and 26 minutes on the outer degree scale. Of course, the scale is not divided so finely, so I'll have to estimate as best I can, but I'm trying to place it a hair under 62.5 degrees. Then I'll find where the thread crosses the rectus scale. It looks like it's right around 88,500. Apian's value from the sine tables is slightly different at 88,647. Next, we'll take the sine of the obliquity of the ecliptic, 23.5 degrees, by repeating the same method. For that, I find a sine of 39,800. Apian, using the sine table, gets a value of 39,874. We take these two sines, multiply them together, and divide by what Apian refers to as the perfect or complete sine. This refers to the sine of 90 degrees, which, again, in his system has a value of 100,000. Doing the math for the values that I came up with using the instrument, I get a result of 35,233. Apian's value is 35,347. In either case, the next step is to convert this back to an angle using the instrument in reverse. To do so, we'll pull the thread across the outer degrees scale, sliding it along until it passes the rectus arc at about 35,233. Again, the scale isn't divided anywhere near finely enough for this to be so precise, but doing my best, I find an angle of about 20 3/4 degrees, or 20 degrees and 45 minutes. Apian's more exact value from doing a reverse lookup in his sine tables is 20 degrees and 42 minutes, so we're pretty close. Apian has essentially the reverse of this calculation as Pronouncement 6, in which he determines the position of the sun in the zodiac, knowing the declination. Let's try another one. There's a very similar calculation for how to determine the latitude of the moon from the ecliptic by means of sines. The calculation here is essentially the same. We're finding the angular distance of a point on a great circle, this time the lunar orbit, from another great circle, the ecliptic. However, in this case, the point of intersection between them isn't fixed by definition like it is for the ecliptic. Rather, the points of intersection between the lunar orbit and the ecliptic, known as the nodes, move. As such, Apian tells us that we're going to need to consult an astronomical table, known as an ephemeridiase. Specifically, what we want to know is how far away the moon is from the nodes on a given date, in the same way as we began when determining how far away the sun was from the equinoxes in the previous example. To describe these nodes, Apian uses the usual poetic convention to describe them as the head and tail of the dragon, which are the ascending and descending nodes respectively. Since the nodes are defined by the points where the lunar path crosses the ecliptic, whenever the moon is at the dragon's head or tail, it is on the ecliptic, therefore 0 degrees above or below it. The maximum distance from the ecliptic the moon gets is about 5 degrees when halfway between the nodes. Apian again provides an example problem, using the position of the moon on the same date as the example we just went through. He tells us that, on this date, the ecliptic longitude of the moon was 23 degrees and 32 minutes into Pisces, while the head of the dragon was 9 degrees and 12 minutes into Cancer. Apian then claims that this is a difference of 45 degrees and 40 minutes in ecliptic longitude. This is pretty obviously wrong, as the difference in ecliptic longitude of the 2 points that Apian gives is actually 105 degrees and 40 minutes. So what's going on here? Pulling this apart, there's actually 2 problems. The first is that the position of the moon given is in the wrong sign. At that time, the moon was in Aquarius, not Pisces. We can chalk that error up to the typesetter choosing the wrong symbol. Thus, the difference in ecliptic longitude between the lunar position and the ascending node is actually 135 degrees and 40 minutes. The second problem is something that Apian just forgot to mention. That is, that we don't really need to know how far the moon is from the node, but how far from the point of maximum deviation from the ecliptic, which is, as we just mentioned, 90 degrees away from the node. Thus, we need to subtract 90 degrees from the 135 degrees and 40 minutes. Making both of these corrections, we can see how Apian arrived at his value, which is the key value that we'll need to perform the calculation. Apian tells us to take the sine of the distance from the maximum, 45 degrees and 40 minutes, multiply it by the sine of 5 degrees, and then divide those by the perfect sine, or 100,000. Let's again try to do this using the instrument. First, we need to take the sine of 45 degrees and 40 minutes. I pull the thread so that it crosses the degrees arc at 45 2/3 degrees, and find where it crosses the rectus scale. It looks like that's about 71,500. Apian again uses a sine table and finds a value of 71,528. Next, I need the sine of 5 degrees, and here's where we run into the limitations of this instrument. When I pull the thread to 5 degrees, it's laying so close to tangent to that part of the rectus arc that it's hard to tell exactly what it's supposed to be indicating. My best guess here is about 8,500, which is pretty good as Apian gets 8,715 from the sine tables. If we multiply our values together and divide by 100,000, we get 6,078. Apian, using the more exact numbers, gets 6,234. In either case, we again convert that back to an angle by pulling the thread taut and sliding it along the degrees scale until it crosses the rectus scale at that point. Doing so, we again run into the frustration of it being so close to tangent that it's hard to tell what's going on. But I get somewhere in the vicinity of 3 degrees. Apian, still referring to the sine tables, gets 3 degrees and 35 minutes. That's a difference of a bit over half a degree. This doesn't sound like much, but it again highlights the limitations of this instrument, as half of a degree is roughly the angular size of the moon. Continuing on, there's still a question of whether the value is north or south of the ecliptic, but that can easily be determined by looking at where it is in relation to the nodes. If we make a quick diagram, we can see that the lunar position is after the descending node, since its orbit is counterclockwise, which means that it is south of the ecliptic. Many of these pronouncements build on one another, with the value found in one being taken as a given in a later example. For some calculations, Apian even gives 3 or 4 methods to find the value, depending on which knowns you have available. Later pronouncements turn decidedly towards geography and cartography. For example, in Pronouncement 66, he gives a method to find the difference in longitude of 2 cities if they have the same object rise at the same time and you know the latitude of each city. One question we still haven't answered is why this instrument works at all. To understand, let's first take a look at where Apian's instrument probably has its origins, in a handheld astronomical quadrant. While the basic versions of this tool only require a set of sights, a plumb, and a scale, astronomers had long realized that there was a lot of space that could still be used for other things. As such, they created the sine quadrant, which does essentially the same thing as Apian's instrument. Indeed, before we cut things out, Apian's instrument was a sine quadrant. Fortunately for this project, I made a mock-up which I left at that stage and we can use to illustrate. In this, if we pull the thread to a point on the 90-degree arc, we can drop perpendiculars to line AB and AC. This forms a right triangle with the thread as the hypotenuse, the one going to line AB as the opposite, the sine, and the line to AC equal to the adjacent, the cosine. In short, imagining it this way is physically laying out what these trig functions are meant to represent. That is the very definition of an analog calculator. Thus, instead of cutting the instrument out to get a fancy shape, we could have drawn in a series of grid lines to allow the user to easily refer back to the scales on lines AB and AC. And many quadrants did so. It should be noted that Apian's instrument could have followed suit and presented the sine and cosine, but Apian reverses the numbering on the cosine scale to use the versine. It's not clear why he did so. That being said, it can be a bit tricky to follow the lines across, and that's the genius of the arcs that Apian used. These effectively took the distances on the scales and projected them onto semicircles so that the thread will always cross them directly. In other words, Apian's method brought the scale to the thread instead of forcing the user to try to follow lines to the scale. But was this really Apian's innovation? In truth, I don't believe it was. To illustrate, here's an early 14th century sine quadrant in the collection at the Smithsonian. See something familiar? While the semicircles are obviously lacking a scale, it's likely that there was another handy feature on the missing thread. If a small bead were added, the user could slide the bead to the point where the wire crossed the semicircle, and then rotate the thread to the scale, making it much easier to use than following the lines. Apian essentially does the reverse in bringing the linear scales to the semicircles. I've yet to find a sine quadrant that actually includes the scales on the semicircle, so I suspect this may have been Apian's true innovation. As Apian closes out this book, he playfully refers to it as a centiloquium. Translated literally, this basically means 100 sayings. But this is also a reference to another centiloquium, which was a collection of 100 astrological pronouncements that, in Apian's time, was believed to have been written by Ptolemy, although modern scholars reject this. He also promises another instrument in the future, designed for students that shy away from numbers. He refers to it as a meteoroscope, and his description of this instrument was finally published in his 1540 Astronomicum Caesarium. So what to make of the Instrumentum Primi Mobilis? As an instrument, it's clever, but not particularly original. Indeed, it strips out numerous features to make a tool that only has a single use, whereas the sign quadrant that it was based on had numerous overlapping functions. And the accuracy, as we've seen, is significantly less than the sign tables which were readily available. As such, this instrument seems best suited to curry favor with a potential patron, especially given that Apian doesn't even take the instrument seriously enough to make use of it in the text describing its uses. Furthermore, those 99 astronomical calculations were likely intended for the same purpose, flexing his broad astronomical and cartographical knowledge in hopes of securing patronage. To my knowledge, Christoph von Stadion never recognized this work or offered Apian any sort of patronage. Perhaps for those reasons, the work has largely been overlooked by historians of science. But I hope that this video has shown a little more about the quirky innovations happening in astronomy before the telescope.